But the question is, what is this? I mean, if you see, you can write this as Fy of y, and the probability that x is less than or equal to y minus a dy. So what is the probability that x is less than or equal to y minus a, that you integrate the p.d.f of x from minus infinity to y minus a actually. So hence, you can also write this expression finally as the c.d.f of the x evaluated at y minus a. So in other words, the c.d.f of x evaluated at y minus a times the p.d.f of y and the integral of it with respect to dy. So we have a generic formula for what do you call the c.d.f of the sum of the random variable, and this formula is this formula actually. Okay, there can be many interpretations of this formula. So this formula, in other words, that if you know the c.d.f of fx and if you know the p.d.f of y, substitute them here and then solve this integral, so you're going to get the c.d.f of x plus y actually. Okay. By the way, if you are doing your course on PDE, or you might have done some courses on linear algebra or special functions, you can also treat this integral as the convolution actually. So this is really a convolution of the c.d.f fx with fy actually. Okay, so this is the convolution of fx with small fy. So you can also treat it as a convolution. Otherwise, you can write it as, keep it as it is actually. Now, if you want to, from this c.d.f, if you want to deduce what do you call the expression for p.d.f actually. So how you can do it? So in order to do it, you need to differentiate this with respect to, say, for example, expression a actually. So if you differentiate with respect to a, okay, so what you're going to get? You're going to get the p.d.f of the sum fx plus y of a equal to the derivative of the partial a with respect to minus infinity to infinity, fx of y minus a, and fy of y and dy. So this is what that you're going to get at. Now, the integral is with respect to the y, and this derivative is with respect to the a actually. So what you can do, you can take this derivative and you can pull it inside actually. So if you wish, you can take this inside. Okay? And do the differentiation into the integral sign. So if you take this inside, in other words, so you do the partial by partial a of fx of y minus a fy of y dy, you're going to get, we call the expression. Okay, so I did one mistake. The value of the x, so there's a mistake in the limit actually. The value of the x on this line is not going to be y minus a, but it's going to be a minus y actually. So it's going to be a minus y everywhere. A minus y should be a minus y, because this was bringing a difference of a minus sign actually. A minus y, and what would be the derivative of fx at a minus y? So you can apply the chain rule and you can compute that this is going to be the fx at a minus y times fy of y with respect to dy actually. So the p.d.f of the sum of the two random variables is really, independent random variables, is really the convolution of the p.d.f of x and, you know, what you call y. So these are the two convolutions. So what we're gonna do at different places, we're gonna use these formula in order to compute the c.d.f and the p.d.f of the sum of the random variables, because this shows that if you know the c.d.fs and p.d.fs of the function of random variables, of the random variables x and y, then you can know easily using these formulas the p.d.f and the c.d.f of the sum of the two random variables. So let's put them in action and let's try to compute, say, sum of two independent random variables, two independent uniform random variables. Okay, so let's just start with sum of two independent uniform random variables. Sum of two independent uniform random variables. Okay. So if x is, say, uniformly distributed with 0, 1, and y is, say, uniformly distributed with 0, 1, I mean, if you wish, you can take a, b, and c, d, and then try to calculate what you call the uniform distribution of a and b, actually. Okay, so for the sake of simplicity, I'm taking x to be uniformly distributed random variables over the interval 0, 1, and y also the uniformly distributed random variable over the interval 0, 1, actually. Okay. So the question is, what is the distribution of x plus y? So what is the distribution of x plus y? This is what that I would like to, what do you call, compute, actually. So in order to compute it, I need to know the four quantities. So what is fx, for example? So fx of x, you're going to say, is going to be 1 over 1 minus 0, so it's going to be 1 when x is, say, between 0 to 1, and it's 0 otherwise. And fy of y is 1 when y is between 0 to 1 and it's equal to 0 otherwise. Okay, so this is what that is going to be. How about the c.d.f of it? Okay. Well, if you wish, you can, you know the c.d.f of the both, just compute the c.d.f of what do you call directly, p.d.f of, you know the p.d.f of x and y both, so let's try to directly calculate the p.d.f of x plus y, because if you know the p.d.f, you can compute the c.d.f as well. So what would be fx plus y of evaluated at, for example, a? So by definition, it's going to be minus infinity to infinity, okay? It's not going to be minus infinity to infinity because these are the things that only exist between 0 to 1. So you're going to say this is going to be 0 to 1, okay? And fx of fy of a minus y times fx of x, and no, this is fx of a minus y and fy of y. Okay. So if your y is between 0 to 1, so what can I say about fy of y? So the fy of y is 1. Is going to be 0 to 1, fx of a minus y, and this is going to be, what do you call, dy.